So our video for day 10. Today we're going to be looking at transformations on tangent graph. So yesterday we looked at transformations on sine and cosine. We're going to look at tangent separately because tangent graph is quite a bit different than sine and cosine graph. So the first thing we're going to do is just go over the basic properties, what our graph for tangent looks like. So the graph on the left, that's one way we can graph tangent. Remember that tangent has a period of 180 degrees, or that's in radians, that's pi radians. And just like with the sine and cosine graphs, we mark off every quarter of the way along the period to make our pattern. All right, mark off 1, -1 on the y-axis, and then we count out our 5-point pattern. So we start at 0, we go to A, then we have a vertical asymptote at 90 degrees or pi over 2 radians, and -A, and back to 0. So going up along the asymptote, then coming down on the other side of the asymptote. The more common way you'll see tangent graph is in between two asymptotes. So starting at -pi over 2 and going out to pi over 2, or -90, +90 in degrees. Right, the pattern's still the same, we're just looking a little further to the left. So here we start and end at an asymptote. For -pi over 4 is our -A. We still have 0 at 0, and A at pi over 4. Right, and then just our basic properties for the function. For our parent function, our domain is everything except for odd multiples of 90 degrees, or odd multiples of pi over 2. So x can't be any odd multiple of 90 in degrees, so 90 times 2k plus 1, or for radians, any odd multiple of pi over 2. So pi over 2, 3 pi over 2, 5 pi over 2, -pi over 2, -3 pi over 2. These are all odd multiples. We have asymptotes at all of those odd multiples of pi over 2. The range, unlike sine and cosine, there's no upper or lower bound on the function. See, along the asymptote, it'll go down to -infinity and up to +infinity. So our range is all real numbers. The period for our parent function tangent is half the period we have for sine and cosine. It's 180 degrees, or pi radians. For tangent, there is no amplitude. We don't have an amplitude. We don't talk about amplitude because it's not a wave. Right? There's no maximum, no minimum value. It'll always go up to infinity and down to -infinity. So there's no amplitude. We do say that our midline, all our 0 points, vertical shift, y equals 0. So it's just a little review, some basic properties for tangent before we start graphing the transformations. The transformations will be similar to what we've looked at before and what we did in the last video with sine and cosine, but our graph is quite a bit different. So we're going to have to look at this a little bit differently with the tangent function. Here's the first example. We're going to graph y equals 2 tangent x over 2. So first thing is, let's identify all the transformations we have. So first thing, we have the 2 out front. Right, this is going to be a vertical stretch on the graph. And the other thing we have is also similar to what we looked at with sine and cosine. We have a frequency. Here that frequency is 1/2. Since we have x over 2, the frequency is 1/2. So for tangent, I'm going between the frequency and period. It's a little bit different. So the frequency is 180 over the period and vice versa. Right, and this is for tangent only. For sine and cosine, we use 360 instead of 180 because that's the period for the parent function. So here, on this example, if our frequency is 1/2, right, we take 180 divide by 1/2. That means the period for this function is going to be 360 degrees, or work with radians, that's the way our examples are, 2 pi radians. So if we want to start graphing this function now on our x-axis, we need to mark off one full period of the function. So if the period is 2 pi, again, we want to graph between the asymptotes to make it easier. That means we need to go back to negative pi and out to positive pi. That will give me 2 pi total, which is one full period of the function. All right, just like before, all our points for the pattern we count out are going to be um, each quarter of the period, which if it's 2 pi, that will be pi over 2, would be every 1/4 of the way along. So again, we'll be starting on an asymptote, ending on an asymptote. Or on our y-axis, what changes our vertical stretch by a factor of 2, right? That's our a value. So we'll mark off 2 on the y-axis and -2. That'll be our a and -a. We count off our pattern. Right, so we have the asymptote, -a, 0, +a, and then the next asymptote. So trace out the curve. There's our tangent graph for 2 tan x over 2. Right, again, if you were using degrees, the graph would look the same, except on the x-axis you'd have marked off 90, -90, -180, +180. Right, but the y-axis would still be the same. So this one, we just have vertical stretch and a change in frequency. We haven't put in the phase shift yet. We can still take a look at how this affects the domain and the range of the function. So for the range, we see it's still going to go down to -infinity along the asymptote and up to +infinity, so our range hasn't changed. It's still all real numbers. The domain has changed. At this point, we see it's no longer odd multiples of pi over 2. We have is now odd multiples of pi. So pi times 2k plus 1, or odd multiples of 180 in degrees. Right, these are the values x can't be. These are where our asymptotes are. Right, there's no vertical shifts. Our midline hasn't moved at all. What has changed, though, is our period has gone from 180 degrees, or pi radians, to 2 pi radians, or 360 degrees. Right, and that came from our change in the frequency. So working through the graphs for tangent, same as for sine and cosine. The difference is we have to be a little more careful with our domain and range, because we have these asymptotes in the tangent function that we don't have with sine and cosine. So another example, now we're going to put in a phase shift. So for this one, we're going to try and graph y equals tan x plus pi over 4. So here, dealing with the phase shift, that's our only transformation on this one. So it's positive. So that means we're going to be moving this left pi over 4 units, or pi over 4 radians. Right, or for degrees, that would be 45 degrees. So again, we'll draw our graph. So we haven't changed our frequency, so our period is still going to be pi radians, or 180 degrees. Right, on our parent function, we'd be starting at pi over 2, or negative pi over 2. On the left for our first asymptote, we're shifting everything to the left pi over 4, so I have to subtract pi over 4 from that pi over 2. Right, so our new starting point, first asymptote, is going to be a negative 3 pi over 4. Right, so we change this to a fraction over 4. Our new starting point will be negative 3 pi over 4. If we have to the left, negative 3 pi over 4. Our full period is going to be pi radians. So if we go pi radians, that's going to put us at positive pi over 4. And you have to mark off every quarter of the way, which is going to be still pi over 4. Right, so all we're doing here is taking the original graph and shifting it to the left, pi over 4. So we're still starting, ending at an asymptote. There's no change. No change in the vertical stretch, no vertical stretch or shrink. So we're still negative 1 and 1 for our A values. And we're going to graph the same way, following the same pattern. We have the asymptote, negative A, 0, positive A, and the asymptote. So again, look at how does this affect the properties of the function. How does it affect the domain, the range? We already talked about the period. So we'll start with the range. Again, for all these tangent functions, we see it's going down to negative infinity along the asymptote and up to positive infinity along the asymptote. So our domain, or sorry, our range still doesn't change. It's negative infinity to infinity, all real numbers. Our domain does change now. So now x can't be pi over 4 or any period multiple of that. So pi over 4 plus the period is pi times k. So any period multiple of pi over 4 is not going to be able to be that. We'll have an asymptote there, so that won't be in the domain. Right, there's no change in our frequency, right, just a 1 in front of the x coefficient for x. Our period is going to stay pi radians or 180 degrees. So last thing we're going to do is just quickly go over 3 more parent functions and look at the graphs of the reciprocal functions. So we'll look at graph for cotangent, for secant, and for cosecant. So forming the graph of cotangent, similar to what we did in the video where we formed the graph for tangent, we know that cotangent is cosine over sine. So anywhere that sine is 0, we're going to have an asymptote. Right, so sine is 0 at 0, 180, and 360. Right, or for radians, that'd be 0, pi, 2 pi. Anywhere cosine is 0, we're going to have a 0 for the cotangent function. So cosine is going to be 0 at 90 and at 270. Or that's pi over 2 and 3 pi over 2 radians. And last thing we know that both tangent and cotangent at 45 degrees are 1. So we use that same kind of A value that we did with tangent for cotangent. So again, we're start off the same, mark off our A, negative A on the y-axis. Here we'll graph 2 periods of the function, so we'll graph out to 360, and we'll have points every quarter of the way along 1 period, so every 45 degrees. Right, so we'll start by using the properties for sine. So anywhere sine is 0, we're going to have vertical asymptote. So 0, that's vertical asymptote. 180, that's vertical asymptote. And 360, that's another vertical asymptote. All right, then we're going to look at cosine properties. Anywhere cosine is 0, we're going to have a 0, so that's 90 and 270. Right, and the last piece we know that tangent and cotangent will be equal anytime they both are positive or negative 1, since positive and negative 1 are their own reciprocals. So the shape is similar to the tangent function, except we see it's coming down from left to right instead of going up from left to right. So it's decreasing instead of increasing. Still has the asymptotes. We see asymptotes occur at different values than they do for tangent, but similar looking shape to the graph. So we're going to look at our properties. We see 2 full periods here, so we know the period for this function is going to be the same as for tangent. It's going to be 180 degrees. For domain and range, we're going to have similar restrictions did for tangent for the range. Again, there's asymptotes. It goes all the way up to positive infinity and down negative infinity along the asymptotes. So we have all real numbers included in the range. For the domain, we're excluding multiples of 180 degrees or pi radians. So integer multiples of 180 degrees or pi radians. Right, then just like for tangent, there's no bound, so there's no amplitude. We don't use amplitude, tangent, or cotangent. And the midline will start at 0. So that's our parent graph for cotangent. For secant and cosecant, we have a trick for graphing these. Makes it a little bit easier to graph these reciprocal functions. So to start with secant, remember secant is the reciprocal function for cosine. Alright, so just like with the tangent function, anywhere cosine is 0, we're going to have an asymptote. So the way we graph secant, you'll see a similar process for cosecant, is we start just by graphing our regular cosine function. So we'll work with radians for this one. We have 2 pi, pi, 3 pi over 2, pi over 2, mark off 1, negative 1 along the y-axis. So for cosine, remember our 5-point pattern is max, 0, min, 0, and max. So we'll go ahead and graph that. So to get from this graph to my graph for secant, what I do is anywhere there's a max, I turn that into a minimum for secant. Anywhere there's a minimum, I turn it into a max for secant, and anywhere there's a 0, I turn it into an asymptote for secant. So start with the zeros at pi over 2, 3 pi over 2, draw vertical asymptotes through there. Minimum at pi becomes a maximum for secant. The maximum at 0 becomes a minimum for secant. Same thing with the maximum at 2 pi. So we see in green is our graph for cosine, in blue that's our graph for the secant function. So go through real quick, look at our properties for secant. So first look at the domain. So we're excluding pi over 2, 3 pi over 2, the next would be 5 pi over 2, and so on. It's all odd multiples of pi over 2 are excluded from the domain. Right, so put that in notation. We said x can't be any odd multiple of pi over 2. So pi over 2 times 2k plus 1. The range, we see everything is included in the range up to positive infinity down to negative infinity, except for this one interval where we find the actual cosine function between negative 1 and 1. Right, none of this is actually in the range of the secant function. So we go from negative infinity up to negative 1, which is included in the range, and then from 1 to positive infinity, 1 again is included in the range. But everything in between negative 1 and 1 is not in the range of secant function. Right, and the last thing, period, we see it goes through the full cycle here. We get half of the upper curve between 0 and pi over 2. We get the full lower curve between pi over 2 and 3 pi over 2. Then we get the second half of that upper curve from 3 pi over 2 to 2 pi. So our period is going to be the same as it is for cosine 360 degrees or 2 pi radians. And last one we're going to do is going to be our graph of cosecant x. That's the typo there. We're going to graph cosecant. So cosecant is our reciprocal function for sine. So just like before we saw with secant, anywhere sine is 0, we're going to have an asymptote. So we're going to use the exact same process we did with cosine and secant for sine and cosecant. So we start marking off our graph the same as we would for graphing the sine function. We go out to 2 pi every quarter of the way. We have a special point. And then we'll make our sine graph in green. So our pattern for sine is 0, max, 0, min, and back up to 0. Now to get cosecant, we use the same process we did for secant and cosine. Anywhere there's a 0, for sine, we're going to have a vertical asymptote. For cosecant, anywhere there's a maximum for sine, we're going to have a minimum for cosecant. Anywhere there's a minimum for sine, we're going to have a maximum for cosecant. So we'll start with all the zeros becoming asymptotes. So that's 0, pi, and 2 pi. The minimum of 3 pi over 2 is becoming a maximum for cosecant, and the maximum at pi over 2 is becoming a minimum for cosecant. So you see the range is going to be the same. The range, all the y values will exclude the interval where the sine function is except for positive and negative 1. All this is not in the range for cosecant. So our range for cosecant goes from negative infinity, comes all the way up to negative 1, includes negative 1, then skips that whole interval, goes from 1 out to positive infinity. If we look at the values that are excluded from the domain, you see it's all integer multiples of pi. We have 0, pi, 2 pi, the next one would be 3 pi, and so on and so forth. It's all the integer multiples of pi. So x cannot be any integer multiple of pi. And just like for secant, graph for cosecant, it comes from the graph from sine, so our period's going to be the same. It's going to be 2 pi radians or 360 degrees. So we won't work a lot with transformations on the reciprocal functions, but they will be part of the parent function bank that you're going to need to know for this class. If you need help with the tangent transformations, you can look for other videos, search for transformations on tangent, or search for tangent graphs.